All right, so question 7M1 from Statistical Rethinking, second edition. Here we are right here. Just a forewarning, you really need to make sure that you have read the chapter or are otherwise familiar with AIC and WAIC, just because the brevity of all of this notation very much disguises some fairly difficult things to understand if you're not already familiar with them. So again, these videos are really meant to be used in conjunction with having read the chapter. But having said that, we will work our way through it. Okay, so we want to compare the definitions for AIC and WAIC, and we'll talk about those in a second, and decide which is more general or broadly applicable maybe. And under what circumstances are they equal to one another, or at least close to one another? Okay, so both of these, AIC and WAIC, are ways of assessing how likely it is that our model, our statistical model, is overfitting the data. Okay, so just a quick recap here. When we are making models, our parameter estimates are picking up some signal and some noise, and it can't distinguish between what is signal and what's noise. It's doing its best, but it can't necessarily tell. And so then when we go to apply that statistical model to data on which the model was not trained, the fact that the parameter estimates contain some amount of noise that will not be matched in the new sample means that the new data may not be as amenable to the statistical model as the training data was. Okay, so in other words, there is a risk of overfitting with our models, and we're trying to determine how much of a risk there is by the use of AIC and WAIC, as well as other methods that are discussed in this chapter, but we won't get to here. Okay. Let's start by looking at the definitions for WAIC and AIC. Okay, so here's the definition for WAIC, okay, where we have the log predictive pointwise density for WAIC, as well as a penalty term, okay. And now the LPPD for WAIC is given here, all right. And roughly what is happening, is for every data point, y sub I, we try to find the posterior probability of that data point given a particular draw from our posterior distribution, right? From the parameter values of our posterior distribution, right? So every draw of our posterior distribution is going to imply a certain probability for having observed y sub I, okay? And then we take the average of all of the probabilities for y sub I, and then for each data point, well, and then we log that, and then we sum that value for each of the data points, okay? So that's what's happening there. And now the penalty term is given here. So again, we take every observation y sub I and its probability given a draw from the posterior distribution. But now as we vary the posterior, or the parameters in the posterior distribution, as we go through different draws for theta values, right, we are taking the variance of this probability, or the log of this probability, right? But in other words, so this should make sense. If our model is overfit, okay, then varying the theta values just a little bit is going to have large impact on the probability of y, okay? So as we go from parameter value to parameter value, the probability of y is going to jump around a lot, which means there's going to be a lot of variance in that term, okay? Which means that we're going to incur a bigger penalty term, right? And so hopefully that makes some kind of intuitive sense. Okay, now on to AIC, okay? So AIC is a little bit simpler, but again, we have the LPPD, and the LPPD for AIC is slightly different, okay? Instead of drawing over all values of the posterior distribution, now we are just taking the point value that maximizes the posterior distribution. That's called the MAP value, or the maximum a posteriori or something like that. But it is the value of theta that maximizes the posterior distribution. Okay? And so then we look at each observation y and its probability given that parameter values or those parameter values. Okay? And then we just sum all of those up. All right. And the penalty term is the number of parameters in the model. So how many explanatory variables we're using to predict the outcome. Okay. So now before moving on, I want to point something out that McElrath is using a kind of a unusual definition here for AIC, and that is here. So McElrath in this book is using the maximum a posteriori, but generally AIC uses the value of the maximum likelihood estimate. Okay, and so then this becomes just a little bit different, but that's okay, and I'm going to address that a little bit later on. But if you're trying to learn about AIC from another source and you read through Statistical Rethinking, if you don't recognize that point, you will become very, very confused, as I did. Okay. So anyway, so we have our LPPD for the AIC and the penalty term, and hopefully this penalty term also makes some kind of intuitive sense. It is just simply the number of parameters, the number of predictors that we're using to predict y. And so again, the more predictors we have, the more likely our model is to overfit the data. And so the more parameters we have, we should incur a penalty, okay? And that's what we have, right? A larger penalty for more parameters. Okay. So, so the things that distinguish WAIC and AIC, of course, are, one, the WAIC is considering the entire posterior distribution, right? We're taking draws over the entire posterior distribution and finding the expected value of the probability of y. Whereas the AIC LPPD is just using a point estimate for the posterior distribution. Okay, so that's one difference. And the other difference, of course, is the penalty term. So whereas the PWAIC, the penalty term for the WAIC, is using variance of the probability of y across the posterior distribution, the penalty term for AIC is just using the number of parameters. Okay, so WAIC is more broadly applicable if for no other reason than it's considering the entire posterior distribution in both terms. Okay, so the WAIC is more broadly applicable. All right, but now we want to know under what circumstances are WAIC and AIC very similar to one another. Okay, so this I am not sure, and so if somebody has a better answer, then do please comment. But this is what my answer is. Okay, so I think that the thing that we need to have is for the sample sizes to be very large. Okay, so when we have very large sample sizes, WAIC and AIC converge. Okay. So let's talk about why this is. Okay, so on one hand, well, so the first thing to recognize is that when we have a very large sample size, the posterior distribution piles up around the MAP value, right? So so the means are going to be the same, right? The MAP is going to be the most probable value of the posterior distribution. So we're going to have a peak of the posterior distribution at the MAP. But as we have more and more samples, the variance of the posterior distribution shrinks until the posterior distribution just piles up all over the MAP, right? So in the limit, the posterior distribution is the MAP. Okay, so that's one thing to kind of think about it. But that doesn't really explain why the WAIC, which has this form right here, and the AIC, which has this form right here, are equal as n approaches infinity. Okay, and so to do that, I think all we need to do is to write down WAIC as n goes to infinity and AIC as n goes to infinity. Okay, so just let's look at these so you can go through the math yourself and make sure that I haven't screwed anything up. But as as n goes to infinity, this first term becomes infinite, right? I'm summing infinite observations, okay, or the log of the expected value. But anyway, I'm summing infinite things, okay? And so that's going to become infinite. And then the penalty term here, as I have infinite observations, well, then my estimate of the posterior distribution becomes increasingly precise to where there is no more variance around the posterior distribution, right? That's what we already discussed. And so there's no penalty. And so then when I multiply -2 times what we have in there, I just get, again, negative infinity. All right? Now for WAIC, it's a similar argument, okay? So again, I'm summing infinite things, so I'm going to have infinity, and now I'm still subtracting the number of parameters. But infinity minus anything that is not infinite, well, or maybe even things that are infinite. I can't remember how all those Cantor rules work, but anyway, if I take infinity minus even a large number of parameters, 100, I still have negative infinity. So in the limit, these two things are equal. Okay, so that's the circumstance. I think the only circumstance in which WAIC and AIC are the same is as the sample size gets bigger. So if you have a better answer, do please comment. I would be very curious. Okay, a final note. Earlier I mentioned that McElrath is using kind of a Bayesian definition of AIC, where he's using the maximum value or the value of theta that maximizes the posterior. But generally what gets used is the value of theta that maximizes the likelihood. Okay, so that's interesting. But the take-home message is really the same. Okay, so if we're in either case, so the maximum likelihood estimate converges to the maximum a posteriori estimate as n goes to infinity, and in which case the same argument just goes through, just as we've already done. Okay, so again, the MLE and the MAP converge as we have infinite data. Okay. So anyway, I will call it good there. You may want to really read through this answer on the Colab sheet just to make sure that you understand what I've done, but also to scrutinize what I've done here. Okay, thank you.